Okay, great. Well, good. Welcome everybody. I'm glad you're here. So today, I think we're really fortunate to have Lace Padilla from UC Merced come speak to us about uncertainty visualization. The genesis of this talk is that Stephen Popper and I were at I think an IAMS conference on visualizing uncertainty, and so Stephen and I did our little song and dance, and then Lace came up and gave a talk. I said, "Oh my God, this is really interesting." Went off read some of her papers, and so just sent off an email and said, "Lace, can you come talk to us at Rayhan?" And she said, "Sure." And we were just talking beforehand whether we've actually met in person or not, which we were unsure of. But in any event, her work is great, and we're really fortunate to have her here. And Lace, I'll let you give any formal, more formal introduction of your affiliations and what departments you're in and things like that, and we'll take it from there. So thanks so much for joining us.
Thank you. I was really excited to see the suggestion that I come talk to the group. It seems like a real interesting interdisciplinary group. So like you said, I'm an assistant professor in the Cognitive and Information Sciences department. So what you're going to hear today is really a mixture of cognitive science and data visualization with a focus on applications for health and policy. So I thought we would actually start today with some data that everyone has been thinking deeply about. This is COVID-19 data that I pulled from last week, and we have weekly incidents on the y-axis, date, of course, on the x, and here was the date from last week. Now, I want you to focus your attention over here to this part of the figure, and we have a mean forecast of what's going to happen for COVID moving forward. So I want you to answer this question for yourself. Is the COVID risk in the US decreasing, increasing, or staying the same? When I look at this, I might say staying the same, maybe decreasing a little bit. Well, what if we change the visualization technique? We can add 50% confidence intervals around the mean forecast. And now the prediction might look a little different, or the interpretation might look a little different. We might say staying the same, decreasing, or possibly increasing as well, if you look at it this way. Now, if we jump up and add 95% confidence intervals, we're starting to see a bigger indication of the uncertainty where really any possible direction is even more likely. As you're starting to see me change these visualization techniques, I want you to pay attention to how your interpretation might actually change. Now, if we show all of the models used to create the mean forecast, we start to get a sense of the distribution of information that's underlying those confidence intervals. This looks kind of crazy, but the nice thing about these types of ensembles is that our visual system is highly evolved to find patterns in complex data. So we can kind of group together where most of those ensembles are shown. And of course, we could add 95% confidence intervals to that. And this is my favorite approach that I'll talk about towards the end, which is rather than showing all of the models, which is a kind of a crazy visualization, what you could do is you could select a subset that meaningfully represent part of the distribution that allows you to get a full sense of what the distribution looks like, but avoids intervals. And we'll talk about why those intervals can be problematic. My point here is that when you're shown these two different visualizations, or really any different representation of uncertainty, you might come to very different conclusions about what your own personal risk is. And you don't get the opportunity to choose what visualization you see. You're just exposed to it from whatever news source you are looking at. And what you happen to see will have a profound influence on your own risk and ultimately what you do. So potentially the health and safety of society. What I'm proposing is the way that uncertainty is presented has a profound influence on our judgments. Now, what I'm going to do is show you this figure to help introduce you to some of the cognitive science that underlies this work. And this figure is a model that describes the visualization decision-making process. It starts here with a visual array, very jargony term for a visualization. It ends here in a behavior or judgment. And I'm just going to focus on this part of the model to start. This is the visual encoding of the stimulus. This is just purely what your eyes can perceive from the information. And I'm also going to use this figure from a chapter that we recently published to walk you through some of the modern uncertainty visualization techniques. These are the ones you're probably most familiar with. These are intervals and ratios. But we're going to talk about how these intervals and ratios kind of interact with the visual encoding of the stimulus. Okay, so here are two 95% confidence intervals. If you look at these and you see them, in a study or online, you might think they're very similar. Maybe they're based on the same data. If you thought that, you would be wrong. They're based on two very different distributions. So right out of the gate, these summaries, which are these intervals, they're summarizing over distributional space. They can hide important features of the data because they're not showing you the full distribution. Now, the reason that can be a huge problem is when you're shown these intervals, what you have to do in your mind is imagine the distribution. You have to create the distribution in your head. And that might look different if it's a 95% interval or a 66 or 33%. It's really hard to imagine those. And I'm showing you some figures on the bottom of different visualizations from different groups who use different intervals. The National Hurricane Center uses a 66% confidence interval. The IPCC in their recent report uses 90, and there was a visualization on the CDC's website that used a 50% confidence interval. My point here is that it is really hard to extract the distributional information from these intervals. And that leads us to our first major concept, which is that these intervals create conceptual categories. It's very hard for us to think about the distributional data. We actually think about them categorically. And I'll give you some evidence from some studies that suggest that that's the case. So here's a type of visualization I've studied very significantly. It is a hurricane forecast, and it is intended to show you the general path that the storm will take. It's based on a pseudonormal distribution, and the edge of the cone is a 66% confidence interval around the mean forecasted path, which is in the center line there. So what we do in psychology is we try to elicit some type of behavioral judgment to sort out how people are understanding this information. And the type of judgment that we want to ask is having people make a judgment that isn't about probability. So for example, I would never say, what is the probability that the storm would hit Louisiana? If I were to do that, I'd only be measuring how good people are at statistics. So we came up with this measure where we showed people a damage scale rating from 1 no damage to 7 severe damage. We would show them a location somewhere on this map and ask them to estimate the damage for that particular location. And this is nice because it's a sufficiently complex decision. It includes uncertainty, and it's something people can intuit. And these original studies, we did them with students at the University of Utah, who are very landlocked, because we wanted to know about just the visual information. How is that really influencing someone's judgment? We don't want to know how much experience these participants had with hurricanes or how good we are with instructions. We gave them very minimal instructions, just a pure visual information. What can people extract from that? So we compare that to a technique that my collaborators came up with called an ensemble display. It's on the right here. And this is an animation showing how they generated it. So what they do is they take the exact same modeling parameters and procedures for the cone of uncertainty. And instead of averaging over that space, they just take one run of the model and plot that. So each one of these lines is one run of the model. And the reason that there's different lines is they're sampling from the perturbation space. They can make small modifications to the model and get all of this sampling. And what this is intended to show you is the general path that the storm will take, not an exhaustive list of every single path. Because we're just sampling from the space, we're not saying here's every single path the storm will take. We don't think it's actually going to swoop around and hit Florida. But if you're just sampling from a distribution, you're going to get some outliers. So that's why you see some of those lines. And that's actually pretty easy to intuit when you see it in an animated format like that. Okay, so what we did is we showed people 2 time points, and our purpose was to determine, can people understand that it's actually easier to know where the storm will be in 2 days versus 4 days from now? So we're hoping to get some data to indicate that there's more uncertainty in 4 days versus 2 days. So that's why we probed these different locations. Okay, let me just move this up here. Starting with the cone over there on the left, I'm going to pull this 4-day time point down here. And we have our damage rating scale from 1 to 7 on the Y. And here's what the data looks like. So one thing that I want to point out to you when you're looking at how these damage scales kind of change is that there is a very steep drop off from kind of right at 5.5 all the way down to probably around 3.7. And that so happens to correspond with the edge of the cone. So people are giving higher damage ratings when the locations are inside the cone and a steep drop off right outside of the cone. So that is indicative of them thinking that there's kind of a danger zone and a safe zone. Now, if we compare that to the ensemble, what we see is a distribution that looks like this, or a kind of a pattern of damage ratings. I want to point out that this just happens to look like a normal distribution with 3 standard deviations. So we don't see these kind of hard boundaries inside or outside of anything. It's really kind of indication that they have a sense of the distribution of probability that we're intending these to show. Now, if we look at the second time point for the cone, and do the same process, look at the data for that. It looks virtually the same to the 4-day time point, just kind of scaled down. And it has the same effect where areas inside of the cone have high damage and areas outside have a very steep drop off. We're seeing the same effect, but the whole thing is just scaled down. They think there's just generally less damage at the more recent time point. And if we do the same thing for the ensemble, the cool thing we see is that for this time point, this looks more like a normal distribution with 1 standard deviation. It's not perfect, but this is giving us some indication that people are aware that we are more certain where the storm will be in 2 days versus 4 days. They can intuit that information from what we've shown them there. And these are the actual figures from the paper. Now, that kind of gives us at least some indirect evidence that people see a danger zone and a safe zone with this cone, and that is not at all what it is intended to show. And they can intuit a normal distribution, pseudo-normal distribution from the ensembles, which is excellent. So this is our evidence that intervals create these conceptual categories in our mind. And why could that be the case? Well, Barbara Tversky writes it nicely in saying, framing a picture is a way of saying that what is inside the picture has a different status than what is outside of the picture. You can imagine if you're an average person and you see someone, a scientist, give you a visualization that has intervals, you might assume that the scientist is trying to say there's something important about the data inside the interval versus outside. But the truth is that interval is arbitrary. We saw lots of different choices of where to place the interval. So people don't understand that there's distributional data. They think that there's something categorically different inside versus outside of the interval. And this, we found this in our work, but almost every time this is tested, people find very similar findings with these intervals. Okay, so that is an example of just the visual information, what it is conveying to people. The next part that I want to talk about are some jargony words that I'll walk you through. One is a graph schema, and another one is a concept called working memory. So here's a figure I'm going to use to help me walk through this. This is a plot that shows the population growth of species X over time, and when a predator species was introduced into the ecosystem. Now, if you're making a fast, snap decision, you might think, oh, well, when the predator species was introduced, that correlated with a drop in the population of species X. So I want someone other than the data viz people in the room to unmute your microphone and tell me why that interpretation is incorrect. Why is it incorrect that when the predator species was introduced, that correlated with a drop in the population of species X? It's also my little drink break. The data viz people too could unmute if you want to.
Well, you have to look at the scale on the y-axis.
Exactly. So for those of you who haven't seen it yet, notice that the y-axis is incorrectly ordered with lower numbers at the top and higher numbers at the bottom, right? So that means that the interpretation is exactly incorrect, that the introduction of the predator species correlated with a rise in the population growth of species X. Now, what I want you to do in your mind is to flip this information, all of it, so that the lower numbers are lower and higher numbers are higher. Give it a shot right now in your mind. Try to imagine that the data is correctly ordered. If you can do it, it looks like this. And of course, you would see the correct pattern. And you might be thinking this is, a bad visualization. No one would ever do this. There's a very infamous chart that does this very same thing. It's trying to give you an incorrect conclusion about the impact of the Stand Your Ground law in Florida and its impact on murders from firearms. Okay, how does this relate to our model? We have this visualization, right? And we have something called a graph schema, which is conventions or rules that you've learned for graphs. And maybe in school you were taught that low numbers should be on the bottom of the y-axis and high numbers should be high. Maybe you just picked it up from lots of exposure to graphs. But in any case, you create the schema in your head, these conventions. And what happens is when you see a new visualization that doesn't match the schema, you have to do a mental transformation to make those two align. And as I had you do that, mental transformation is quite hard. It requires working memory. That's the cognitive science word for effort. It is just hard to do. And we're going to talk quite a bit about effort throughout this. And this is just an example of how when you have to do a mental transformation in your mind, you have to reconcile the schema with the visualization. It requires working memory. Okay, so looking back to these visualizations that we have here, the other big thing that we find with these cone-like versions is that people think that they represent the size of the storm growing over time, and they don't communicate anything about size whatsoever. But consistently, people think they show the size of the storm. And so our big question is, well, why is that the case? And what we're thinking is that it has to do with the schema that I just discussed, how schemas work. Now, when you look at these hurricane forecasts, they are on a map. So you use your schema that you've developed for maps. And one of the rules that we've learned for maps is that physical area on a map in some way relates to area in the real world. We're even taught when we're little that we can get out a ruler and measure distances and then do some simple math to approximate the distance in the real world. Now, if you were to do that with this cone, you would be completely wrong because the distance in no way pertains to physical distance. It pertains to something abstract like uncertainty. So what we'd have to do to get this correct is we would have to remap the physical width of the cone to the abstract concept of uncertainty, and that requires mental effort or working memory. So this is really an example of how these schema errors, when we're asking people to do something with a visualization that doesn't align with how they would naturally do it, schema error, we're seeing some mismatches there. So the next one that I want to talk about with this is when we developed this new ensemble technique, it was new, so we weren't fully sure what type of schemas people would be using when they saw this ensemble visualization. So what I did is I surveyed the visualization techniques out there, and it occurred to me that one that people are familiar with is a route-based navigation application. And the schema that we've developed for this, or the strategies, are that you're shown possible routes from one location to another. You're shown a list or a set of possible trajectories that you could take. You're not shown a distribution. Now, if you were to use that strategy you developed for these route-based applications to interpret the ensemble, you'd be quite wrong. You essentially think that we're showing you every single path that the hurricane could take. So that could lead to some errors. And so that's really the question. Are people using this schema for routes to interpret this ensemble display? Okay, so here's a simple illustration. Here is a hurricane forecast with 3 paths that we're showing, and one of them hits your home. I want you just to imagine what is the probability that this hurricane will hit your home. Just think of it in your mind. Now, you're all probably recognize that this is a trick, but I bet the first thing you thought was 33%, and then you modified it in some way. Okay. Compare your estimate for this one to this one. Is it more or is it less? You can all probably see now that there is something special about when one of those lines directly hits a point that you care about. It makes you feel more nervous. Even if you know that we're intending to show a distribution, it just seems kind of scarier when one of those lines hits your home. But as I said before, the meaning of each of those lines isn't that important because they were pulled from a sample. We're not saying the hurricane's going to go down, could go down each of these paths equally likely, that it's just sampled. So the way we wanted to test this is we showed people these hurricane forecasts, and we set it up where there was 2 locations on a map, and one was always directly on top of one of the lines. I just drew it in darker here for you. And then we would ask which location would receive the most damage, location A or B. Now, in this case, if people would believe that areas kind of closer to the center of the distribution would be in most danger, they should say B almost 100% of the time. And yes, they do say B virtually 100% of the time. But if we change the context and have the further location, having that one be the one that's on one of the lines, what do people do? Well, if they continue to think that simply the location that's closer to the center of the distribution should receive the most damage, they should still say B 100% of the time. But if they think that it's possible the storm will go down that one single path and hit A, they'll say A some percent of the time. People say A 36% of the time and B 64% of the time. So they do, in fact, think that there is some real important chance that the storm will follow any of these specific lines. So this is, one of the ways we can get an indication of how the type of schema that people use to interpret these ensemble displays. Okay, so that leads me to my third big point, which is schema misalignments can cause error. Anytime you're making a new visualization technique, you need to be very careful that you're not evoking a schema that leads people to the conclusions that you didn't intend them to, which is the case with many types of uncertainty visualizations because it's abstract. Okay, moving on to another part of the model, let's talk about the decision-making bit and some more about working memory. And to be clear, I've alluded to this throughout the talk, but just to be direct, these visualization techniques are summaries of distributions, and all of these ones here are distributions of distributions. So the real question that we had was, given that you have distributional data, and then you have to transform it, summarize it to get these summaries. If you have to do a task that involves uncertainty, in your mind, you have to transfer that back to a distribution. And does that whole process in your mind require extra effort or working memory? So we wanted to do a study where we looked at the impacts of working memory when evaluating these visualizations. Okay, so this is inspired by some work that I've done with the Red Cross. And my collaborators told me of this event where in 2005, there was a cold snap in the high mountains of Peru. And this led to just under 100,000 alpacas dying due to freezing temperatures. So their job was to create a forecast-based financing system to help to determine when to issue emergency aid to these alpaca farmers. And they were wanting some support in terms of finding the best way to communicate the forecast distribution, both for themselves and for the alpaca farmers. And what would happen is they would issue aid in the form of blankets or cold weather protection if the temperature was forecasted to go below a certain temperature. Okay, so the task was, assume that you work at the Red Cross and your job is to manage resources for farms in Peru. In previous years, alpacas have died in Peru from cold temperatures. They can typically withstand temperatures unless they drop below 32 degrees. And your job is to consider the forecast and determine if the nighttime low will drop below freezing. Okay. So here are 2 types of distributional visualizations that we showed people. The top one is a density plot. Bottom one is a quantile dot plot. Just for yourself, I want you to think about this question. What is the probability that the temperature will be 32 degrees or below? If we did this with the density plot, you'd have to find 32 degrees and mentally calculate the integral under the curve. It's very complicated. This is nice because we see more of the distribution, but identifying any specific value is quite hard with density plots. And we call these density plots probabilistic framing because they're communicating probability in percentages, whereas we could visualize virtually the same information, but with a quantile dot plot, which uses frequency framing. So it'd be saying 1 out of 10, which is frequency, versus 10%, which is probability. The way these work is that each one of these dots represents a 5% probability. So what you could do for the quantile dot plot is simply count up the dots. You could say there's a 5, 10, 15, and somewhere between a 15 and 20% chance that the forecasted low would be below 32 degrees. And we can work backwards using a probability density or cumulative distribution function to identify the exact value. So it's actually 16% probability. And we were pretty close, right? Between 15 and 20, and the true probability was 16%. Okay. So what we presented participants with was a scenario where they had a budget, and we wanted to have a correct answer in this experiment. We don't always have correct answers, so in this one, we wanted to. The way we set it up is that they had a budget for their Red Cross of 18 days of $18,000. Blankets cost $1,000 per night. The penalty for not issuing blankets if the temperature does drop below 32 degrees is $6,000. And they would get an extra 10 cents for every $1,000 left in their budget. Okay, and based on this incentive structure, there's an optimal strategy. So I'm going to show you data that is about accuracy because we could calculate it directly using some very simple math. Okay, and these are the 5 visualizations that we compared. I already showed you the quantile dot plot and the density. We have a 95% confidence interval shown in a plot. We have the same information but in text. And then we have a visualization of the mean with no uncertainty whatsoever. These, of course, are the distributional visualizations, as I am really hitting home. And these are the summary annotations, the summary communication of that same information. Now we had some other types of conditions where we varied the variance and we randomly showed that to people. Now the way that we got at working memory, if you're not familiar with this type of thing, is we had an individual measure of someone's working memory capacity. The way we did this is we had a very standard test called an O-span, where people would do a math problem, and this would be on the screen for 5 seconds. And then they would answer the math problem, true or false. And then they would be asked to remember an object and do another math problem. So they would be doing a sequence of these math problems interleaved with remembering an object. And their goal was to remember the order of these objects. So at the very end of the experiment, they had to recall the order that they saw the objects in. And what this allows us to do is to have a measurement of how much information they can store in their mind. It's actually a measure of their working memory capacity. And I won't go through the details of this, but we got error scores for their working memory capacity. We have a measurement of their working memory. Okay, and we ended up splitting people into high and low working memory capacity groups, which is the important part for this. And here is the actual data from this experiment. What these are posterior distributions from a Bayesian analysis. And basically, the way to interpret these is how much overlap there is means that there's not a lot of difference between the groups. But I'll walk you through this. So the groups are based on this working memory measure, the O-span. That's how we got the high and low groups. Low is in purple and high is in green. The probability of a correct response is based on this alpaca task, and we have the 5 visualizations there. The first thing I want to point out is for the 2 distributional techniques, we're seeing the best accuracy if you collapse across high and low working memory groups. So right out of the gate, they're just eliciting the best performance, these 2 distributional visualizations. There's a meaningful difference between high and low working memory for the quantile dot plots and for the means. So what I'll point out for that is the people that had high working memory capacity, who could remember the most information, they did the best in all of the scenarios when they saw the quantile dot plot, which is really cool and significantly better than those with low working memory who also saw the quantile dot plots. The people who had low working memory did about the same as those with high working memory who saw the density plots, which is interesting. Now for the mean, the important thing to note is that individuals with low working memory, those who could use the most support, they did the worst when they weren't given any uncertainty information. So that uncertainty information is really helpful for people with low working memory capacity. Now I'm going to show you the direct comparisons between each of these groups just to highlight some of these findings. On the left, we have the high working memory group. And what we have going on here is that these icons indicate the comparisons. So what you're seeing is the Quantile Dot Plot compared to the mean, the Quantile Dot Plot compared to text, Quantile Dot Plot compared to interval, and so on. And the ones that are highlighted in green have a meaningful difference, meaning that the Quantile Dot Plot was better than all of those other visualization techniques if you have high working memory capacity, which is pretty cool. Okay, if we look at for people with low working memory capacity, what we see is that both the density plot and the Quantile Dot Plot did better than all of the other ones. So cool. But there was no meaningful difference for people with high working memory capacity between the Quantile Dot Plot and the density plot. That's telling me that if you have high working memory capacity, you can capitalize on the additional information given to you by that Quantile Dot Plot. But if you don't, if you have low working memory capacity, you're going to treat the Quantile Dot Plot the same as the density, which is fine. Both have highest performance compared to the others, but just note that they're most beneficial for those with high working memory capacity, which is pretty cool. Okay, so that leads me to my next conclusion, which is that with distributional data, consider using distributional visualizations. They have the best accuracy, and they also are useful for people with a range of working memory capacities. Okay, last thing I'm going to do is start where I began. I'm circling this whole model because I'm going to talk about COVID data, and it's a very complex decision that I think involves every element of our model. Now, we did COVID study back in October of 2020, and much like many of you, we didn't anticipate that COVID would be going on for 3 years. So what we wanted to do was to test every possible visualization technique for COVID data because we thought we would never have the opportunity again. So what we did is we pulled real COVID data and live visualizations, and we asked people to estimate their risk after viewing the actual COVID data for their state. And we have it kind of grouped because we had so many different visualization techniques, but we had some controls where we didn't show people forecast data. We had a version where we showed the mean without uncertainty. We had some summary visualizations and some distributional visualizations that we tested. In some, we had 16 groups for this first study back in October. And I'm going to show you some data from the most interesting ones. I won't show you the data for the whole thing, but I'll also show you the graphs so you can see what those look like. This is cumulative death data from California, and it shows a mean with a 50% confidence interval. So at the time, the cumulative data was going up, and there is a little teeny interval there, but it's very certain that it's going to keep going up. And we can compare that to an incident scale. Now, the cumulative data is sort of always adding up, essentially, but an incidence scale is just showing you the number of reported deaths for a 2-week interval. So it can go up and it can go down. This is what you're classically shown on the news, these incidence scales. And we have a 50% confidence interval here for that. And note that this one and this one are the exact same data. The only difference is the choice of how to plot the y-axis. Now we have, this is a 50% confidence interval. We also have 6 expertly selected models. They're grouped together on top of each other for this version with the cumulative data, but you can see them spread out more with the incident data. And we had an expert forecaster on our team, and she selected these models to represent the distribution, and because they had minimal model assumptions about kind of the data that went into them. And we compare that to a version where we had all of the different visualizations, all the different models, and here's what all the different models looks like here. Okay, here are the types of questions that we ask people. We ask people to evaluate the risk to themselves and other people of some various effects of COVID. So for example, one question was, how often do you think each of the following people will come in contact with someone currently infected by COVID in the next 2 weeks? they had to rate that for themselves, an average 22-year-old in their state and an average 78-year-old in their state. That was one type of question. They also had to answer the likelihood of coming in contact with COVID, having severe adverse effects from COVID, and the risk of being hospitalized from COVID. Now, they did those risk judgments at the very beginning of the study, and we didn't tell them anything yet. We just had them make those judgments. And then we showed them one of those visualizations I showed you in some previous slides for 2 minutes. And they were forced to watch it for look at it for the full 2 minutes. And then we had them do the exact same risk judgment. And nothing changed about the risk judgment whatsoever. Now, I'll be the first to say I didn't think this would work. I didn't think that people were going to change their risk judgments. We originally did this just to get a sense of how people understand these visualizations, but we didn't honestly think that with a 2-minute exposure to a visualization, people would change their beliefs about COVID, because at that point they had been, hearing about it on the news for months and months, and your internal beliefs about your own risks are pretty stable. So it's a very tall order for a visualization. And then we took lots of measures of other stuff, including their age, gender, education. On the CDC's website, they had health risk factors for COVID, which were 20 possible health effects that you could have that would make you more susceptible to COVID. We have their graph literacy score if they had ever contracted COVID or had been tested for COVID. So the data I'm about to show you is after controlling for all of those significant variables, but we controlled for those statistically. And the data I'll show you is after those effects have been taken out. Here are the results of just the impacts of the visualizations. Okay, so we have the mean that I showed you with no interval. Then we had a 50% confidence interval, one with 6 models and one with all models. And this is for the cumulative axis. This is what the data looks like. I didn't have shoot. I just changed these slides. Actually, I'm going to just skip ahead so you can see the scale. There we go. At the very bottom, notice the risk scale going from 1 to 7. But I'm going to step back to walk you through this. So these are the estimates before people saw the visualizations. And then after they saw the visualizations, this is how the risk judgments changed or did not change. And I'll note that for the 6 models and for the all models, people meaningfully increased their risk estimates. So we have no meaningful impact of visualization exposure when we have a mean and 50% confidence interval, but the visualization increased people's risk perception for the 6 and all models. And I'm going to add the scale in here just a second. Sorry, I didn't put that in there. And these dotted lines that I have represented here are the average across all of the visualizations that I haven't showed you, across all the other 16 visualizations. So just to give you an indication of how people changed from pre-visualization exposure to post-visualization exposure for the cumulative y-axis. Okay, there's our actual scale. I just updated these figures. Our paper actually got accepted a few days ago, so I updated this with our new figures. But we compare this to the incident y-scale, and we're seeing some very different things going on. Really no meaningful impact of visualization exposure whatsoever. Nothing interesting going on. The only thing that's sort of happening but isn't significant is that with a 50% confidence interval, people are becoming more risky. They think they're under less risk when they saw that visualization technique. The biggest finding from this work is the difference between these dotted lines. So what this is sort of suggesting is that there's a larger increase in someone's belief about their own risk when they see the cumulative y-axis compared to no meaningful increase when they saw the incident y-axis. So why is that the case? Maybe you saw it when I showed you the figures initially, but there's some big differences here. For the incident y-axis, the data happens to be going down. And for the cumulative, it happens to be going up. So the actual trends are just in different directions. And that just happens to be when we sampled the data. It could have been that the COVID trend was going up at that particular time, and we could have had a more direct comparison. So there's a confound in our experiment. And what we ended up doing is looking at the data again once we realized this. I noticed that for California, We still have this kind of upward, or I'm sorry, at that point, there was an upward trend for California for the incidence scale, and the same thing for the cumulative. But for New York, it was relatively flat. Because they had a very big peak early on, the data for both their incident and cumulative scales looked relatively flat. So we basically redid the exact same study. The only thing that we changed were the visualizations that we showed people. And we did this with people in California and people in New York. So we could get a sense of the effect of the recent trend in the data. Okay, so here's the data for that. I'm going to add in these plots just so you know what they correspond to. And first thing I'll point out is that for the New York data, there is no meaningful impact of visualization exposure, which makes a lot of sense because those are the data that have flat trends, most recent trends. But for the California data, both the ones with the steeper upward trend showed the largest increase across these visualizations. So we're seeing that same people believing they're under more risk after they saw the visualizations that had that upward trend most recently. The other thing we did is we replicated our previous work suggesting that with the 6 model forecast, people were more likely to have a larger increase in their beliefs about their own risk, and that meaningfully larger increase than the other visualization techniques that we showed. It's kind of leading us to this general conclusion that with the cumulative y-axis, it leads to less variable judgments. We basically found that people's judgments are really influenced by the most recent data. And with an incident axis, you can artificially change the direction of that trend. If there was more testing all of a sudden because, the CDC issued a bunch of tests, it could artificially go up. Or if it was a holiday, it could artificially go down because there was less testing. So it's highly variable. And if you wanted a more stable risk perception by the public, you might want to use a cumulative y-axis. The other things we learned is that with distributional data, consider using distributional visualizations. We found that with this study and all of the previous ones I've shown. We've also learned that schema misalignments cause errors. And finally, we've learned that intervals create conceptual categories. So with this, I hope I've given you lots and lots of evidence that the way that uncertainty is presented has a profound influence on our judgments. So with that, I want to thank my co-authors. These are just the co-authors from the 2 papers that I kept returning to, but there's dozens of co-authors that are not listed here. So thank you to all of those. And I'm happy to answer questions. And I'd love to hear your own insights of experiences with COVID data if you have any.
I have a quick question, if that's
sure.
okay.
Yeah.
Go ahead, John, and then we'll pick up Pedro.
Okay, thank you so much. So my question's about the nature of COVID itself and how it is has evolved, and how so it's evolved. We have vaccines, we have other measures to inform and protect the public. What does that do to your visualizations and the underlying data over time?
You do see those in here. So maybe I could go back to the recent data. So part of what's going on here is, we're seeing when vaccinations started happening, and we're seeing when an Omicron wave kind of picked up. So that is absolutely represented here. And from what the experiment that I showed is that people tend to be most influenced by the recent trends. But in my experiment, we didn't have such a long history of COVID. Like this type of up and down is very different than what we actually tested, this kind of thing. There was some patterns. So it's unclear what happens if there is a longer history, if we would see the same impact of the recent trends. It might be reduced. It might be that when people are looking at, this, wherever it went, this type of thing, they start to get a sense of the patterns. And so they're going to make different types of predictions. Imagine that it would go up and down, up and down. But I do suspect that people will focus mostly on the recent trends, and that will be at least biasing their decisions. I don't know that for sure, though. That's just some speculation.
Pedro.
Hi, Lace. Thanks for the talk. This is just very, very good. So, being having modeled COVID for the past year and you kind of working with this data is just fascinating to me how that changed people's decisions. And I have many questions, but let me focus on one, which is one of the reasons why I've seen some papers like the COVID-19 Scenarios Hub publishing confidence intervals as just as a region. One of the reasoning, a rationale for that, one of the rationales is that we're really not confident on the probability distribution of those outcomes. We really don't trust that, given how we calibrate our model to past data, the distribution will reflect, for example, a new variant and so on and so forth. So it might be like if scientists are not confident on those distributions, would you think actually the intervals are more appropriate? Because I do see some trade-offs there, right? If we're not confident on that distribution, then yeah, maybe we shouldn't communicate a lot of confidence on that distribution.
I think there's a difference between so there's no inherent information in this visualization that conveys the confidence in this distribution, this interval itself. So whether researchers were confident or not, that is not communicated to the public. So I see why they might suggest that they don't know about the distribution, but they're inherently making some visual claims, if you will, that there's in this one, this kind of, if you didn't know what the distribution was, you would say it's sort of a skewed distribution, right? You're still going to try to imagine that distribution. So I think it's a little disingenuous to say that if we don't show the distribution, that means that there's no indication. There still is if you're showing an interval, but people are just going to make up their own. So do you want to have them, the viewers, at least give them an indication of something that's reasonable to show, or do you want them just to make it up because you're uncomfortable, suggesting what it is? The other thing I will say, though, is like this is not necessarily a predictive distribution. This is all of the models that created the ensemble. So this isn't as if you show this to people, I don't know that it's saying that we've calculated this distribution. What it's showing is that there's disagreement amongst different models from different groups. And that is meaningful. So I think if they are worried about not knowing the distribution per se, I think this would be a more honest way to convey that uncertainty. And I mean, I didn't look at it closely until you mentioned it, but this could be a little bimodal. Maybe some models are kind of grouping up here or down here. But that might be a way to get around that nervousness about not being able to accurately predict the distribution given new variants. But good question.
Okay, thanks.
Great. Rob, and then we'll pick up Dawn after.
Great. Where's my camera? There we go. Great. So thanks. That was really great and fascinating. So I actually have a general question, not a COVID question, but this is a virtual room full of people who are always making uncertainty visualizations and sticking them into presentations and reports and decision tools and all that sort of stuff. And so you had a couple of very specific takeaways, so like don't use the distributions, use the frequency plots, etc. But what would you recommend, for people developing and putting together, these visualizations as part of what they do all the time? I mean, is there, do we get your handbook and that has like a list?
It has a little bit in there.
Yeah, I mean, obviously the ideal thing to do would be to run extensive studies every time on every option you're looking at. But when do you know you have to do that? When, what's your advice?
My main advice is that I think don't be afraid of showing the uncertainty. Number one, you just got to show it for both because it is helpful for people with a range of abilities, and it's important for scientific credibility and trust, so forth. So show it. You probably all do, so that's fine. Preaching to the choir here. But my next recommendation is if you can go with some type of frequentist visualization. I didn't really, lay it out in that super great detail, but these Quantile Dot Plots have had the most support from my work, Matthew Kay's work, Jessica Hallman's work, over and over again. These tend to be the most successful technique if you can use them. There's not every case where you can have quite this much information. And why people don't show them is they're afraid that people will find them confusing. And we have yet to find that in any of our studies. So be brave. Go ahead and use a Quantile Dot Plot if you can. I didn't make the choice of using the Quantile Dot Plot to present this research, for example. I just went with a density plot. So in this is how I visualize my uncertainty data. Well, I have to have a confidence interval because I did a frequentist statistic, but I also included a density plot to show the relative distributions there. So I kind of had there's trade-offs, right? Sometimes you have to include something that's not ideal, like an interval. But then if you layer in some of the distributional information, so it's at least there for people, that's how I've solved these kind of trade-offs of how to do it. And of course, I would say when at all possible, try to do these judgments horizontally, because our visual system has an easier time detecting differences in a horizontal plane versus a vertical plane. You usually see this kind of flipped where you have a box plot and error bars going horizontally. That's a harder visual judgment vertically than the horizontal. So that's my general guidance. Of course, I don't always stick to it. I'm not having dot plots here. But another good idea is just to follow Matt Kay and Jessica Hallman's work as well. They're really fantastic. They always come up with new studies every year that give you little pointers each year that will get you closer and closer.
Great. Thanks.
Mm-hmm.
Great. Don.
Yeah, so Rob, first I want to thank you for pulling in this speaker. It's a fabulous talk, and her for giving us the time. I will say in the early days, I did my own analysis because that was the only thing I trusted till the data got better. But my question for you is, how did you choose the people that you took part in your experiments? I mean, in the old days, you would get volunteers from universities, and that's, of course, a very biased group. So I would imagine your results potentially could be affected by who you did the experiments on.
Yes, definitely. So I showed you a range of different groups. The hurricane work, we did those with students at the University of Utah. I didn't tell you this for the other studies, but those were all online with populations of either Mechanical Turk or prolific. This particular study with the COVID data, because we did this most recently, we can do things like control to make sure that the population actually represents a distribution that's has male and female balance, has a population scaled representation of different races, ethnicities, different beliefs, which is really cool. So at least this study is controlled to ensure that's as most representative of the U.S. population as possible. But that's certainly not the case with some of the other work that I showed with university students and so on. But it is something that is becoming more and more of an issue when we have more options of different people to work with. But it's a really good point. I haven't talked about this in any study, but my favorite parts of these data are all of these things. The analysis of age and gender and education and COVID. Yeah, it's a really cool part. There's I think like a 50-page supplemental material that accompanies this paper that digs into all of these really important factors that influence our risk. It's good to note, or at least that's we're very sensitive to the impact of the different groups of people that could be participating in this. So thanks for bringing that up.
Thanks again. Wonderful talk.
Thanks.
So we're almost at the top of the hour, and I don't see other hands. So I just want to ask one question about you seem to give some inkling that like the 6 model, right, the expert model for those trajectories was a preferable way or was a more effective way to represent those possibilities, right? As opposed to showing all the models or just showing one. And it strikes me that that's one of those, okay, which models are you going to pick problems where,
Yes.
it's a perfect opportunity for bias to creep in if somebody wanted to manipulate opinions, right? Because you definitely, you had that bimodal distribution, easy to say the 6 expert models, right, were the 6 that pointed straight up. And
yeah, that's a good point. Yes, no one's brought that up yet. I haven't given this talk many times. The way we try to frame it is in intelligently selected models. We have not done the research to figure out what that means. If that means that you ought to, select, that there should be some rules about them representing portions of the distribution. I feel like that should be the case. What we did is we had these for specific model parameters, but I think there's a lot of different ways to do that. I was just talking with the Defense Ministry, and they kept indicating that they wanted one that was always the worst case scenario, even if it doesn't like anyway. So
that's
you can
horrible. Yeah.
Exactly. But they insisted that was necessary.
Yeah. I know.
So a lot of work needs to be done in terms of guidance on how to select these. But you're right. For all the guidance in the world, people could select all the ones that they want to indicate whatever they want people to do.
Right. And
go ahead.
Yeah,
Don.
go ahead, Don.
I was just wondering, something just occurred to me. Did you see this morning's New York Times that had all these probabilities of the amount of snow that was going to fall on the East Coast?
Oh, no, I
They
didn't.
had bar graphs on the front page. Did anybody else see that? Ed, you usually read the paper. You should take a look at it.
I'll have to look at that. That'll be interesting.
Well, we're at the top of the hour. Lace, thanks. This was awesome. I dropped into chat. We actually, we did some research some number of years ago on air quality, and we did a quantile dot. One of our students did quantile dot distribution for air quality sensors. So this was awesome. I feel like I nurtured my inner Tufty in this talk.
Always a good thing to do.
Yeah, and it's fabulous to actually have data behind the design decisions that you make, because I think, these are, your data visualization is a combination of, there's the rigor in the math, but you're making design choices on the color that you choose and the line weight, and, I love the flipping of the axes. Again, it gets towards this, how do you, are you trying to propagandize what you're doing? And I think the answer is that everything that we do is some form of propaganda. It's just a question of how much intent is in there. So good deal. Thank you again. And we'd love to have you back if you're game to tackle another aspect of the visualization stuff, because this is an ongoing problem that'll never get fixed.
Yeah, absolutely. Anytime. Thanks so much for inviting me.
Great. Thanks so much.
All right. Thanks, everyone. We'll see you in 2 weeks.